Hello everyone, welcome back to my channel. So today as we are discussing about the electromagnetism, so in that topic we are going to discuss about the electromagnetic induction, or also called as the Faraday's law, and we are going to discuss about the Lenz law. So let us see about what is these two two laws, what are these. So let us see here. So first is the electromagnetic induction, which was discovered by the Michael Faraday. So Michael Faraday, the one who discovered, who invented the electric motor, the electric generator, and also we can say the transformers. So all these were invented by Michael Faraday. So on his name, he has made it a law which is called as the Faraday's law. So here he concluded that whenever there is a continuous change of magnetic flux, as I told you, the magnetic flux, nothing but the magnetic lines. So when there is a continuous change of magnetic flux linked with a closed coil, an induced current is produced. So that is what we can say here is, so we have taken a copper coil, so which is a copper coil, wound it around, and the copper coil is connected to the galvanometer G. So what is the use of the galvanometer? So here the galvanometer is used to find out the detection of current, that whether the current is present or not. So to find out the presence of current, we need to have an instrument which is called the galvanometer. Now we have taken a bar magnet facing the north pole, or maybe you can take it as south pole, and when we insert a bar magnet into the copper coil, inside the copper coil, so when we insert it inside the coil, so then there is an induced EMF, that is a current is being produced into the coil and the galvanometer gets deflected. So how that happens here? Simple, as if you take the bar magnet, so this is the bar magnet, north pole and south pole. So there is a magnetic field lines which are present around the north pole and the south pole, as we know this. Now when we bring it near to the copper coil, so when we bring it near to the copper coil, these magnetic lines get linked with the copper coil. So when these magnetic lines get linked with the copper coil, so the electrons, that is the charges which are present in the copper coil, starts to move, that is they start to move from one place to another place. So when they start to move from one place to another place, that is nothing but we call it as current. So as the charges move from one place to another place, so and current is being produced, that is what we call the induced current. So in the induced current is being produced over here. And again when you remove it from backward, again these magnetic flux these are being linked with the coil, and again the charges try to move in the opposite direction. So that opposite direction that we will see in the Lenz law over here. So definitely when a bar magnet is been inserted into the coil, there should be a continuous change of the magnetic flux. That means if there is no change, like suppose this is a copper coil, so this is a copper coil, and suppose this is a bar magnet. Now when you insert it inside, so it gets the magnetic flux gets linked with the coil, and an induced current is being generated. Now again if I keep it like this the same way, then as there is no change in the flux, the current will not be produced. Again if I move it backward, so again there is a change in the flux, again there is a induced current. So in a mathematical form, how can we say is, there is another definition here, that is the induced EMF, that is electromotive force, the induced EMF generated in a closed loop. So this is the closed loop. So the EMF which is generated in a closed loop is equal to the rate of change of magnetic flux. So rate is nothing but the time. So the rate of change of magnetic flux. So delta represents the change over here. So the induced EMF, that is electromotive force, EMF is equals to the rate of change of magnetic flux. So for example, if we take for the N, this is for one turn, that is for one coil, one rotation of a coil. But if we take more number of turns of coil, then we write it as a formula EMF E is equals to capital N, that is the number of turns, whether it is 1 turn or 50 turns or 100 turns, is E is equals to N delta phi by delta T. So this is the mathematical notation for the Faraday's law. So I will show you at the end of this video. You will be seeing a video about the demonstration about how does the needle which is present in galvanometer gets deflected, that we will be seeing here. So that is about the Faraday's law. So when there should be a continuous change, then only an induced current will be produced. So this principle works for the electric generator. Now let us see over here when coming to the Lenz law. So what is the Lenz law is? So the Lenz law is the induced current, the current which is produced here, the induced current will appear in such a direction. So it will appear in such a direction that it opposes the change of flux in the coil. So it opposes the change of flux in the coil. So what means the opposing the flux in the coil? That let us see here. So I have a galvanometer here. So initially the galvanometer is at the 0 position. So this is the positive values and these are the negative values. And here I have a copper coil. So this is the copper coil and this is the bar magnet. Now the bar magnet is going inside the coil, that is I am inserting inside the coil. Now due to the magnetic flux, that is due to the magnetic lines, these are being linked with the copper coil, and the charges which are present due to this motion, that is due to the force, this magnetic lines, the magnetic flux gets linked with the charges. So the charges start to begin to move from one place to another, which brings the induced current. That means a current is being produced. So that when the current is being produced, again this needle which is in the galvanometer move on to the positive direction. It moves to the positive direction when a bar magnet is inserted into it. So when a bar magnet is inserted into it, then suddenly what happens? When a bar magnet is inserted, you will be keeping like this. So there is an oppose in the flux. So why there will be an oppose in the flux? As there is an oppose in the flux, again the needle which has went to the positive direction again came back to its initial position, that is it came back to its 0 position. So why does it come like that? So simple. So when you insert a bar magnet inside the coil, the magnetic flux or the field which is linked with this makes the charges to move in a particular direction, right? So when they move in a particular direction, as we know, the moving charges or the current which produces the magnetic field, right? Now the magnetic field which is produced in this copper coil and the magnetic field which is produced by this bar magnet both link together and opposes to each other, and they may oppose each other and the current becomes 0 here. Again when you turn it back, when you are coming in backward direction. So when you are coming in a backward direction, so the current again moves to the negative direction. So as the current moves on to the negative direction, so when the current moves on to the negative direction, the motion of electrons which are moving from here this point to this point before, now when we coming to the backward, it comes in the reverse direction. So as we are coming back, again the flux which are being linked to this the charges which are present in this copper coil, they make the attract, that is they attract the magnetic field of the bar magnet. So when they come to attract, they come to the negative direction. This all what you have to remember is when we insert a bar magnet, it moves on to the positive direction, and as the current is being produced, it produces a magnetic field around it. That magnetic field will oppose the magnetic field of the bar magnet. So due to that opposing, there is a change in the flux. So that is the reason why it comes back again to its original position. So when it is been inserting into it, it moves on to the positive direction. Again when you remove it, again it comes to the negative direction. So this is about the Lenz law. So in for the state syllabus, for the CBSE, they don't have the Lenz law, but for the state syllabus they have the Lenz law over here. So in your textbook you might have seen this diagram over here. So if you might have seen this diagram, as the copper coil, that is the coil which is the when a bar magnet is inserted into it, so a current is being induced into it. So how can we find out? So in some of the examinations they may told to find out this, like this is one type of an exercise for you. So this is one of an exercise. So there is a bar magnet which is facing the north pole and it is being inserting into it, and there is another one which is facing the north pole, which is coming in backward direction. Now you may not get to this your public examinations or all, but for your further intermediate, that is the +1 +2, in your +2 syllabus you will get it to find out, and you will be having an exercise about to find out the direction of the current. That before to learn it's a little bit better. It's very simple also. So remember one thing, when a bar magnet is coming near to the copper coil, so this is the copper coil, when the bar magnet is coming near to the copper coil, it should be repelled. Remember that it should be repelled, and when the bar magnet is moving away from that, then it should be attracted. So remember these 2 points, then automatically you will find out the direction of the current, that whether it is coming out of the page or into the page, that you will be finding out here. Clear? Now remember that the direction of the magnetic bar magnet is coming towards that which is coming near, it should be repelled. Keep in your mind that when it is coming near, it should be repelled. When it is going away, it should be attracted. Just like a relation between a wife and husband. Okay, just it's just joking over here. So when it is coming near, it should be repelled. When it is going away, it should be attracted. Now here, when it is coming near to the copper coil, it should be repelled. That means if it is being repelled out, that means here we are having a north pole facing. So that means it can be repelled only when there is a north pole facing only. Now what you will do is, here just place the north pole and opposite direction will be the south pole. Is it clear? As the north can be repelled only with the north, so you just place out the north and the north over here, in the south and south on the opposite direction. So as we have a thumb rule, right hand thumb rule. So right hand thumb rule, remember that in a circular loop, and I told you these curved fingers represent the direction of the current and the thumb represents the direction of the magnetic field, right? So you need to remember one more thing, that the thumb indicates the north direction and the tail indicates the south direction. Do you got it? So whenever you place the magnetic field with the thumb in upward direction, or wherever the thumb is being present, so wherever the thumb is being present, that is the north pole, and the tail will be the south pole. Now if you observe here, so this is the north. Now forget about this. Now this is the north pole and this is the south pole. So north pole should be faced with the thumb and the tail with the south pole. Now here it should be coming out of the page, and coming on this side should be entering into the page. This side should be enter. So 2 parts here. See, this side should be out. That means out of the page we represent as a dot, and into the page we represent as into. That means here it will be having an into, and here we will be having an here we will be having dot, and here we will be having into. This is the same representation we got it here, right? Now in this case, so this is a copper coil. Now it is moving away. When it is moving away, it should be attracted. Now can you tell me what pole should be placed here for attraction of north pole? Yes, we have to get a south pole. If you keep a north pole, then that will be repelled. That doesn't make a sense to this. So it should be attracted. So as we are having a north pole, it should be attracted with a south pole, and opposite it should be a north pole. Simple, just a north, and this side it will be the south. Now what you have to do is, again place your right hand thumb rule. So where is the north present? So north is present on the left side. So flip on your thumb finger. So this is the north, and here it is going upward it is going into the page, and down it is coming out of the page. So as it is going into the page, so we keep it as into, and it is coming out of the page, so we keep it as dot. So another one exercise we can see, I can show you here, and you need to answer this before I reveal the answer. I will give you the time to reveal the answer. So we have a circular coil. This is a circular coil, and the north pole, and this is the south pole and north pole, and it is going away of the coil. It is going away from the coil. Okay, and at the same time, so another coil, and we have a bar magnet, north pole, south pole, which is coming near to the coil. Now can you tell me the answer for this? So you see the direction as it is going away. As it is going away, it should be attracted. As it is going away, it should be attracted. So that is going away, it should be attracted. So here we have a south pole. You should not move on, don't look on ways to the north. The coil which is, the pole which is facing to the coil, that is important over here. So here we have a south pole. So south pole is attracted with a north pole. So that means on this side, on this surface, it will be the north, and on this surface it will be the south. Now place your right hand thumb rule. As the north direction is on the opposite, so just place your thumb on the opposite direction, and here on the upside, on the upper side, we will be having a out of the page, that is which is coming out of the page, so out of the page, and on the downward it is going into the page, so we represent it as dot and here as into. Now coming to this, I'm giving it to you. So here we have a south which is coming near. When it is coming near, keep in your mind that it should be repelled. Now what we'll get here and what we'll be getting here, I'm leaving it to you, you answer it. Yes, so here we'll getting a into, and here we'll be getting dot. How can we say that? As this is the south pole, so as it is coming near, it should be repelled. That means it should be repelled means here the surface should be the south pole, then only it can be repelled, and here we have a north pole. By placing your right hand thumb rule, so up will be the into and down will be the out of the page. So these are the just a small exercise for based upon the Lenz law. So this may not be useful for your public examinations, but this is very important that you may get a clear understanding. If you know about this exercise, then you will get a clear understanding about what is meant by Lenz law. So Lenz law is nothing but it wanted to become it is going to be increasing to the positive value, but due to the opposing, it come back again to the zero. Again it is going to the negative value, again there is an oppose, and again it is coming to the zero. Okay, clear? That is what meant opposing. There is an opposing change into the flux due to the magnetic flux between the copper coil and the bar magnet. So this is about the electromagnetic induction, that is the Faraday's law, and also about the Lenz law. Now in the next we will be seeing that the working model of the Faraday's law with a copper coil. It is a small activity over here. So here we have a number of turns, so with a single turn, 100 turns, another 1000 turns, and these are been connected to a ammeter, and so you can see the ammeter which notes the reading of the current, and these turns are being connected with the help of the clips. The black one is the negative and the red one is the positive, and a north pole facing bar magnet is been inserted into it. So as you can see the slight deflections over there, so that is due to that when the magnetic flux of the bar magnet, when it is being linked with the copper coil, it produces an induced current. So due to that induced current, again it produces a magnetic field around the copper coil. Now the magnetic field around the copper coil and the magnetic field around the bar magnet gets opposed to each other and come back to its original position. So as if you observe here, when you insert it with a more amount of force, it produces more EMF, and when you keep it inside it, so there is no EMF. See, there is a zero current over there. Again when you remove it back, it comes to the negative. When you insert it inside, then it moves on to the positive direction of the current. So observe carefully the movement of the needle which is present in the ammeter. When we insert a bar magnet, observe the variation. Now coming to the 1000 turns, now here you will observe it very carefully, very clearly, that when we insert a bar magnet, you observe the induced current. See the movement of the needle. When you move it back, it moves into the negative. When you push it inside, it moves into the positive direction. And this is the DC current which you are getting here.